So in this slide, we can see the rapid acquisition can be attained using the GRAPPA algorithm, which is a parallel imaging algorithm. And let's see how we can use this algorithm in inversion recovery curve mapping. So here again, you can see the k-space time point, let's say n-1, and you have acquired the first and the third and so on peripheral k-space lines, and you low lines of the peripheral k-space, you perform the same subsampling there. And here you are not using any sort of linear interpolation in between time points, and you can use the acquired data and then apply the GRAPPA algorithm for reconstructing the missing data at the same time point. So GRAPPA algorithm can be used also for the rapid acquisition. And we can combine the line sharing and GRAPPA algorithm. And here the trick is that you acquire the first line and then you miss the two k-space lines, and then you acquire the third one, and so on. And after acquiring the data, you are first applying the line sharing process so that you can reconstruct every other k-space line at each time point. So the red dots are showing the k-space lines reconstructed using the line sharing. So after applying the line sharing, we can see that we are in the situation that we can apply now the GRAPPA algorithm for the rest of the missed k-space line. So here actually you have enhanced the speed by a factor of 2, and you are using two algorithms, line sharing and GRAPPA, with just one after another. First you are applying line sharing and then the GRAPPA algorithm. And so here are the processes described in case you want to simulate these algorithms. First, you acquire a series of full raw k-space data from each coil, and then subsampling of the k-space data in the phase encoding direction, and according to line sharing scheme which I have described earlier, or GRAPPA. And then after that, at the reconstruction stage, you apply line sharing or GRAPPA algorithm. Then you have series of modified k-spaces, and then you apply the inverse Fourier transform to reconstruct the images at different time points along inversion recovery curve. And then the T1 map of single slice is fitted using Levenberg marked algorithm for accurately reconstructing the T1 map. And all the time points acquired are used for generating a single T1 map. So now there are the results. After applying the line sharing algorithm, the line sharing is applied to tapier data acquired at 4 Tesla with parameters of TR 20 millisecond, TE is 2.5 millisecond, and tau is 2000 millisecond, flip angle is 26 degrees, and I think the bandwidth is around 800 hertz per pixel. We can see on the slide, and 500% the slice gap slice thickness is 2 millimeter, field of view is 256 millimeter by 256. EPI factor is 1, and 20 time points were used with the keyhole size of 32 by 32 and matrix size of 256 by 256. And here are the results using the grappa algorithm. The same, the bandwidth was, the same parameters were used as it was in the previous experiment. The bandwidth was, which was unfortunately, I think, not clearly visible in the previous slide, it was 700 hertz per pixel. So, and the keyhole size again is 32 by 32, and in parallel imaging literature we call it ACS lines, or auto-calibrated scan lines. And here are the results when line sharing and grappa both are applied for rapid acquisition, and the acquisition parameters are the same. So here are the results, and you can see that actually, if I go back and just mention that in every slice we can see the red region mentioned with red block, then yellow block, and then green block. The percentage difference between the reconstructed T1 map and the original tape-year T1 map, it was calculated and mentioned in this graph. So we have observed that in region of interest 1, tape-year, grappa, and line sharing, and combined line sharing and grappa algorithm, they all performed almost with a difference of like less than 1% or less than 2% in the case of, let's say, region of interest 3. So all algorithms, grappa or line sharing or line shared grappa, can be used to enhance the speed of original tape-year sequence. And here are just a result for another slice number 3. And here the observations are similar as they were in the previous slides. Now I am going to describe the method for processing phased array data for rapid relaxation mapping. And the motivation is that in certain cases, phase or amplitude errors can occur in case space. Such errors can induce artifacts, for example, field of view divided by 2 ghost artifacts in the reconstructed image. Phase array processing method, which is also known as the full field of view sense method, can remove possible artifacts due to amplitude or phase errors. And this full field of view sense is a modified method of a parallel imaging technique known as sense. And mathematically, we can see how much it is different as compared to original sense method. If, let's say, the desired magnetization we want to reconstruct, it's denoted by F, and S denotes the complex field sensitivity from, let's say, ith coil, and you can observe either 1 ghost or 2 ghosts on the reconstructed image finally. So if it's only single ghost, then n is equal to 1, and the ghost spacing is basically it's also equals to field of view divided by 2, and we have made this factor as 1 before. And n is the observation noise, and h is weight of kth ghost arising from signal at the spatial location denoted by x and y. So if you compare this set of equation with standard sense equation, then you can observe that it is not applied to the half field of view. It is applied to the complete image, to the full field of view. So you have just taken the basic equation of sense and applied to the complete field of view image. And in the equation notation, we can write it like this. And we know if we invert it, because we are interested in finding the magnetization. So it would be like F is equal to multiplication of unmixing matrix and the data which we have acquired. So S of X and Y is estimated by correlation. Actually, this is the sensitivity, which is estimated by the correlation of low resolution images reconstructed using the central case-based data. And in parallel imaging methods, we always need, in sense, we always need a sensitivity estimation. And in this algorithm, that was obtained by using the low resolution images reconstructed using the central case-based data keyhole. And now we can calculate the matrix U, the matrix R, and then apply this method. And this method is basically applied to phantom, but we have done 5 different experiments, and in every experiment, the percentage of gadolinium, which is used to enhance the relaxation rate, that was increased. So if we see, let's say on the first column, this is a T1 map of the phantom. It's reconstructed by using a single coil method. And in the second row, the percentage of gadolinium is increased, so relaxation time is supposed to decrease. And here in the third row, the percentage of gadolinium is increased more as compared to the case before. And similarly, in the fourth row, the percentage is higher, and in the fifth row, it is the highest. So in the columns, actually, other methods are used. The simple multi-coil sum of square method was used to combine the images coming from different coils. And in the third column, the array processing method, which was described earlier, that was applied, and then T1 map was fitted. So we can see that as the percentage of gadolinium increases, the relaxation time gets faster. There's more chance of observing the n/2 ghost artifact, or field of view divided by 2 ghost artifacts. You can see in this case it is pretty much visible, and the ghost is actually highest in the last case. And if you see, let's go to the first slide again. If you see, in the case of multi-coil sum of square combination, we can observe in the third row that somehow it tends to reduce that field of view divided by 2 ghosts. And in the array processing method, it is supposed to reduce the ghost artifacts, not completely, but to the maximum extent. And the similar array processing method was applied for reconstructing the T1 map using the array processing method and comparing with standard tapier. And here are the regions: the red region, the yellow region, and then the green region. The relative error was calculated as compared to the standard tape here, and you can see the relative error is below 1.5%. And in the last section of this lecture, I want to talk about a rapid motion estimation scheme. So what is the problem? How can we state the problem? In the case that the data acquisition is fast enough to freeze the intra-shot motion, motion occurred predominantly in the image plane. So these are the two conditions. If they are valid, then we can say that the rigid body motion and the two-dimensional rigid body motion, or simply in-plane motion, it can be estimated and corrected. In this case, the motion affected image can be considered as the rotated or translated replica of the corresponding reference image. So let's say if the first image here, it is the reference image, then if rotation occurs, then the replica image will be rotated. The reconstructed image after the motion would be rotated replica image. And if translation occurs either in X direction or Y direction, then the reconstructed image after the motion would be translated replica image of the reference image. And the motivation for rapid motion estimation is that the pseudo-polar Fourier transform is applied, and the angular difference function, which is related to the processing after the calculation of pseudo-polar Fourier transform, actually this we consider as a useful approach for real-time motion correction, because it is very fast in terms of computational power and time. The method is without any interpolation errors, and the computational complexity is the same as applying single FFT if we talk about the pseudo-polar Fourier transform calculation. So that's the motivation that we want to move towards the algorithm which can be used for the real-time motion correction. And as I explained in the initial slide, that two kinds of motion errors could be present in an in-plane motion case, and first is in-plane rotation. And as we have casted the whole problem in the polar coordinates, and case space in polar coordinate and in-plane rotation in the polar domain can be represented as you can see in this equation, that if a body is moved to an angle, then that angle will be added to the previous angle in a polar coordinate system. And P1 is the magnitude of reference case space, and P2 is the magnitude of the rotated case space. And in Fourier transform dependent schemes, rotations are reduced to translations on the polar grid and be recovered by correlation. And polar grid computation uses the FFT algorithm, whereas the interpolation in the polar FFT computation is always inaccurate. So instead of using the polar coordinates, transition from Cartesian coordinates to pseudo-polar coordinates can be performed directly according to these formulas. And there's a reference which I have cited here if you want to look at the derivation of these calculations, you can use that paper. And here F is the Cartesian case-space representation whose coordinates are basically linearly transformed to pseudopolar coordinates, and M and N are variables. These are actually the points, the sample points along the grid. So actually, if you have, let's say, Cartesian coordinate system, and you have applied one-directional FFT, a one-dimensional FFT in the y direction, then you have the coordinate which is ky, which is a Fourier variable, and along the x-axis you have the same spatial variable x. And similarly, if you apply a one-dimensional FFT along the x direction, then you could get the spatial frequency variable kx along the x-axis, but along the y-axis, the spatial variable remain the same as y. And in the first case, after this process, you apply the fractional fast Fourier transform in the x direction, then you get the grid of this kind. Now you are completely in spatial frequency coordinates kx and ky, and the transform points look like this on the grid. And similarly, in the second case, you apply fractional fast Fourier transform in the y direction, and you get this kind of grid and spatial frequency coordinates. And if you combine these two grids, then the pseudopolar coordinate system can be represented like this. So this is pseudopolar grid and spatial frequency coordinates. And the difference function is described here. There's another reference for just looking at the details of derivation of this equation, but the simple idea is that you could subtract the two pseudopolar coordinate systems, and you could get the amount of rotation, and it was coming after like this. The angle, when you subtract it and use these equations, and the angle is basically can be computed from the angle corresponding to the minimum of a function which we termed as an angular difference function in the previous equation. And if you find the minimum of this function, then you could find the angle. And the idea was that you could reconstruct the low resolution images from the acquired data, and then you calculate the pseudopolar Fourier transform using the low resolution images, and then you calculate the angular difference function, and then you apply the inverse rotation to the images to correct for the rotation that was occurred. So for this process, basically you need one reference image and the other one is the rotated image. And for the translation estimation, a linear phase shift in k-space, it produces a linear displacement in a certain direction in the image space. So if you see this equation, then you can see that if an image is moved either in x direction or in y direction, then it corresponds to a linear phase shift in k-space. So here's the k-space, and this exponential, it represents a linear phase shift, and xn delta x and delta y are the linear displacements in the x and y axis direction. And if we calculate the cross power spectrum, the normalized cross power spectrum, using the k-spaces of the reference image and the translated image, then using that normalized cross power spectrum, we can further decompose that that matrix, which was termed as M before. So M can be written in the form of two vectors, which we have defined in this manner, and there's a reference to the derivation of these equations as well given here. And the problem of finding the lateral shift between two images is now recasted as finding the rank 1 approximation of the normalized phase correlation matrix M. And a simple approach to find the dominant rank 1 subspace of M is to use the singular value decomposition method. And this is just these are the processes involved. And so the idea is that you are using images as navigators. At the post-processing stage, you should have a low-resolution reference image and low-resolution translated image, and you calculate the phase correlation matrix, and then you apply the single value decomposition, and then least square fitting of left singular vector and right singular vector is performed separately, and we could find the horizontal displacement from the left singular vector and vertical displacement using the right singular vector. And this is the complete data processing flow diagram explained for the combined translation and rotation estimation scheme. That you could use keyholes with different sizes, but let's say for the smallest keyhole, first apply the inverse fast Fourier transform. You get the low resolution image, and then you use these low resolution images for calculating the translation parameters, and you can use the same low resolution images for calculating the pseudo-polar Fourier transform grid, and then applying the rotation estimation algorithm. So that's how you can achieve the rapid motion estimation algorithms. And the conclusion, if I conclude the whole lecture, the acquisition time of the tapier sequence, it can be further reduced by up to 40% using the line sharing approach. In addition to that, the concept of sharing the k-space lines can be extended to combine line sharing with parallel imaging. And then the proposed motion estimation scheme has low computational complexity and is therefore suited for the real-time motion correction.